Cool. What is chemistry then? Chemistry is a way of describing our universe. In order to describe something, you need words to be able to do it. Words like chemicals, and atoms, and molecules, and compounds, and in particular, elements. We're going to be looking at some different elements today. I'm going to start by having a look at this diagram, which shows you that your body is made up of mostly of 6 elements. Those elements are oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. They are the 6 main ingredients that make up the entirety of you. What we're going to focus on first is hydrogen. Hydrogen is known as the first element because of the way it is made up. Can anyone tell me what is an element made of?
The same, but it's the same thing.
Atom.
Yeah, you're on the right line. Someone's saying it over here as well.
Nitrogen and water.
Wow, that's there are some elements. We're going to look at those later on. What did you say? Atoms. Yeah, elements are made up of atoms, and they're all the same type of atom. So you were getting that. Okay. So, what are atoms made up of then? Yeah. Yeah, specific names. I'm looking for. There are 3 names, 3 things in an atom. Any ideas?
Neutrons.
Neutrons is one of them. Fantastic. Neutrons. What else?
Electrons.
Electrons. Brilliant. And
Protons.
protons. Fantastic. Yes, atoms are made of protons, neutrons, and electrons. Electrons, which are negatively charged, orbit around a nucleus which contains protons and neutrons. And the negatively charged electrons are kept in place by the positively charged protons. So, look at this. This is an example of a hydrogen atom. You can see that it has 1 proton in the middle. It's got no neutrons at all, and 1 electron that goes around in a shell. Can anybody tell me how many electrons can fit in the first shell of an atom? Does anybody know? 2. Brilliant. So, hydrogen needs either to gain or lose that electron to be stable. It needs to gain 1 electron to be stable. Okay, this is hydrogen. We're going to have a look now at another element. The next element has 8 protons, 8 neutrons, and 8 electrons. Any ideas what element this might be?
Oxygen.
Oxygen, brilliant. Oxygen, this is oxygen. So we can see the nucleus in the middle with its protons and neutrons. It's got 2 electrons in that first shell. That shell is full. How many electrons has it got in its outer shell? How many is it? 6. Yeah. How many electrons can fit in an outer shell? The outer shell is known as the octet. It can have up to 8 electrons in it. So for oxygen, it wants to gain 2 electrons to become stable. So if you were to take 2 atoms of hydrogen and 1 atom of oxygen and mix them together, what would you get?
Hydrogen oxide.
Yeah, you can see what you're thinking about it, but it's a bit simpler than that.
H2O.
H2O, which is water. Yeah, water. You get water. Yeah. Now, hydrogen doesn't exist as single atoms. It exists as molecules, which are 2 hydrogen atoms that are bonded together, sharing electrons. So, what we would need is it's known as a dihydrogen molecule. We need 2 dihydrogen molecules and 1 oxygen molecule, because oxygen also exists as 2 atoms bonded together, sharing electrons. If we mix them together, we would get 2 lots of H2O, 2 lots of water. Okay, we're going to take a bit of a closer look at the 3 compounds that we just talked about: hydrogen, oxygen, and water. We're going to start with hydrogen. In this balloon, I've got some hydrogen gas. What we're going to do is we're going to pump this gas into our bubble mixture just here, and then we're going to add a bit of energy. We're going to add some fire. What do you think is going to happen?
Explode.
A big flame. Explosion, shall we find out?
Flame.
Yeah. Alright, here we go.
Or set on fire.
Okay.
Is this all bad?
We've got our hydrogen bubbles in bubbles. We have got, hopefully, a flame.
It's gonna be
So
flame.
let's see, here we go. 3, 2. Try again.
Round 2.
Ready? 3, 2, 1.
Whoa.
Okay, what happened to our hydrogen?
A little flame.
Blew up. It ignited, didn't it? It caught on fire. It burnt away. That's because hydrogen is a fuel. It's quite a dangerous fuel, but it can also be very, very useful. We use it for things like powering rocket ships to send rockets into space. All right. Let's have a look next then at oxygen. Oxygen's a much bigger molecule, so what do we think is going to happen to the oxygen if we do the same thing? What do you think? Explosion again. Do we agree?
No, I'm just gonna go on fire.
Yeah? I think so. Should we find out?
It'll be a bigger bubble, like an
Yeah.
explosion.
It'll be a
Okay,
bigger
let's
fire.
find out. Here we go. We're going to put our oxygen.
More
into
fire
our
and a
bubbles
bigger
as well.
explosion. Oh. Yeah. Looks like washing up liquid.
Yeah, that's what it
Okay. Got our flame. We're going to add in 3, 2, 1. Oh, what's happening?
Just burning away the bubbles.
It's burning away the bubbles. Burning away my candle as well. We didn't get an explosion like we expected. Why? Well, oxygen isn't a fuel. Oxygen is a catalyst. It's something that speeds up a reaction. So, when we added oxygen bubbles, all we got was a bit of a brighter flame. It didn't have a bigger reaction, it just reacted a bit quicker. See, it's burned away quite a bit of my candle. Alright, one more thing that we're going to try. We're going to try, there we go, hydrogen and oxygen mixed together. What do we think is going to happen this time?
Explosion. Oh no, it's gonna be a big fire.
Big fire. Yeah, so we had
Like
had
gasoline
the ignition
and
of the hydrogen, and we've got oxygen now to speed up our reaction, which means that we should get a much bigger reaction. This is the point at which you're going to want to put on your earphones. Okay, everybody got the one? Yeah. Excellent. All right, we're going to add our hydrogen and oxygen.
It's louder. It's louder.
I can hear it. Oh no.
Louder.
I can hear it bubbling up.
Okay. In 3, 2, 1.
My heart stopped. Oh God. Oh my God.
Okay, that's it. No, that's
When we have our oxygen and hydrogen gas together,
Did you feel it? The
Yeah, you can
explosion.
feel it.
That's why, you know when there's a big explosion, you know when
The wave.
you know all the breaks in the buildings, that's all that wave, it's yeah.
Frequency wave.
if we want to combine elements, we need to do more than just put them together. They
Sorry.
don't just form water straight in the bubble. We need to add energy if we're going to combine elements. Okay? Excellent start. All right.
Smoking.
Now, earlier on, somebody mentioned this. What was this called? Periodic table. Fantastic. Yes, and it sounds like you've all seen it before. In fact, you've probably seen it in every science classroom you've ever been in.
Yeah.
Yeah. Campus events, okay. It's just one little bit. It will stop itself. Don't worry. Thank you very much for letting me know. Yes, you've probably seen periodic table in every science classroom that you've ever been in. It is a brilliant way, a very elegant way of organising all the different elements. And just by knowing how the periodic table works, you can look at the position of an element on it, and learn an awful lot about it. We're going to have a look at some of the different elements on our table now. We're going to start with the left-hand side just here, group 1. Now, you can see that hydrogen, even though it's at the top of group 1, it's left-hand column, sorry. Even though hydrogen is at the top, it's a different colour because it's not actually part of group 1. It's a little bit too different to be part of the group 1 elements. But these, the rest of them, are called the alkali metals. And they're all quite similar.
Yo, RB. RB.
Okay. Okay, so these are our group 1 elements. They're known as the alkali metals, and they're all quite similar. You can see they're all quite shiny. They are all very reactive. They react with water, they react with air, they react with acids. In fact, if you name it, they react with it, yeah? Good question?
You know when that explosion happened?
Yeah?
Like what actually happened? Was it just a shock wave or did something like this explode?
So it was the hydrogen that was burning, but it just burned really quickly, much quicker than we did it when it was on its own. It was the oxygen. If you didn't have your head, your defense on it, probably would have hit your ears a bit. Yeah. Hopefully not definitely, but okay. So as we were saying, alkali metals are very reactive. They react with everything, which means they are quite dangerous. If we look at the other end of the periodic table, group 17, we have the halogens. The interesting thing about the halogens is that when they're in their gaseous forms, they are all visible. We can see all the different gases there. And whereas our alkali metals in group 1, they all have 1 electron in their outer shell, just like hydrogen. Our halogens, however, all have 7 electrons in their outer shell, which means that our alkali metals want to lose an electron to be stable, our halogens want to gain an electron to be stable. Now, we're going to think about chlorine, which is the second one on the left-hand side there. And chlorine is a very dangerous element. In fact, chlorine gas was one of the first gases tested during World War I. And it is particularly horrible because if you breathe in chlorine gas, it reacts with the mucus in your lungs and throat and creates hydrochloric acid, which you definitely don't want. Okay, if we were to take one of our halogens, our chlorine, with 7 electrons in its outer shell, and mix it with one of our alkali metals, say sodium, with 1 electron in its outer shell, we should have a fairly interesting result. This is something that's a bit too dangerous for us to do here in the science theatre, so I'm going to show you a video on this one just instead. So, watch this.
He's getting stuff for the next thing, is he? Yeah. Thanks. It looks better on video.
Okay, can anybody describe the reaction that you just saw? What happened first of all? Yeah, the fire got really bright. It was bright, lots of heat, lots of light. What else? We notice anything else? Did we see the vapor trail coming up?
Yeah.
Yeah?
It was like heating something up, so it's gonna turn it from a liquid to solid.
Possibly. What we had there were 2 things that were mixing together. We were mixing a gas and a solid together, heat. And what did we see at the end? What was produced? Yeah, some sort of white crystal, wasn't it? Any ideas what that white crystal was?
Powder.
It was definitely kind of a powder. But what was it? We mixed sodium and chlorine.
Rock crystals? Sodium chloride. Yeah.
Sodium chloride.
Fantastic, yeah. The product was just table salt, the kind of salt that you put on your chips, just like that.
Oh.
But from some things that were very dangerous, sodium and very dangerous chlorine gas, mix them together, and you get something that's actually quite safe, that we eat regularly. Yeah.
What's the big gas canister? Very big.
They're for you to wonder about until the end of the show when we use them. You will find out.
Oh, God.
You will find out what everything is for at some point during the show.
Yes, we're gonna all explode and
what we're going to do
die.
now is we're going to focus a little bit more on our alkali metals. So that group 1 elements. There we go, our group 1 over on this side. We're going to look at 3 of them in particular. Lithium, sodium and potassium, which we've got little bits of on this tray just here. Now, they're all in group 1, which means they're all very similar in the way that they their appearance. They're also similar in how they react, but there is one difference, and we're going to look at that difference now. We're going to start by adding our lithium to water. Here we go. So the reaction, we'll talk about what happens in a moment.
Hold them up. Which one is it? All of them?
Okay, what do we notice what's happening to our lithium?
Vapor.
Smoking, yeah, there's something coming up, isn't there? Cooling down. Actually,
It's heating up.
This is an exothermic reaction, so there's actually heat being produced in there.
Yeah, it's heating up.
It's heating up, yeah, and it is.
Steam.
What's actually happening to the metal? It's gone now. Where's it gone?
It burns.
Dissolved, yeah, it's dissolved into the water, and we said that there was something coming off. There was a gas being given off. We're going to think about what that gas might be in a moment. But let's move on to our next one. We're now going to add some sodium to water. So, here we go. Let's see what happens with this one. Okay, got more fizzing. It's moving around a bit more violently, and what did we see at the end there?
Pop.
pop, and a bit of a flame. Yeah, fantastic. So, a similar reaction, but slightly more violent this time. And again, we had that gas being given off. Anyone got any ideas what that gas might be?
Hydrogen.
Hydrogen, yeah, fantastic. Where's that hydrogen coming from? Do you know? Okay, go for it. I can think of it again. No, probably not. We've had the one big loud noise, so you can just pop them on the seat next to you. Alright, so we had our metals, they're dissolving in the water, we've got a gas coming off, and in this case we had a bit of a flame. We said that gas is probably hydrogen. Where's the hydrogen coming from? From the water, yeah, absolutely. Alright, let's have a look at our final one, and this one is potassium. Now, what do we expect to happen with potassium? Think an explosion? Yeah, shall we find out? Here we go.
Whoa. It was purple.
Yeah.
Is it because it's cold water?
Alright, so we
It's all
had
hot.
a bright
Remember we
pink
did
flame in our
fireworks?
case. We had again more gas
Did you
being
do
given off, more
fireworks yourself,
hydrogen
or was that
coming
lyrics?
from the water. And
Fireworks.
reaction there, a bit of a pop at the end. So what this tells us is that elements in the same group on our periodic table react similarly, but as we move down the table, they get more and more reactive. And we said that hydrogen was coming off. The hydrogen was coming from the water and was being given off as a gas when our metals were dissolving. So our metals are still in there, but they're now forming part of a hydroxide, which is what happens when water loses that hydrogen element. Now, hydroxides are all alkaline. Have you heard the word alkaline before?
Yeah.
Yes. What's the opposite of an alkaline? Acid. Fantastic. And can anybody tell me what is an indicator? What's an indicator? Yeah.
Oh, it tells you.
Yeah, it changes colour in the presence of alkalis or acids so that you can see what is in
Red
them. There are
if
lots of
it's
different
red.
indicators. I'm sure you could have learned about them in school. This one is called phenolphthalein, and this one turns bright pink in the presence of alkalis. So we can see that all three of our hydroxide mixtures are alkalis. If we wanted to turn them back to clear, what would we need to do?
Acid. Add acid.
Add acid. Absolutely right. We've got some acid just here. And if we pour it in, we can see that it turns it back to clear. Does anybody know what that's called, that process? Yeah, neutralization. Fantastic. Alright. Okay, let's pop these down here for a moment. Because we're going to move on now. We're going to think about some of the other metals on our periodic table. Does anybody know how many of these elements are metallic? Or how many plastics?
Metallic.
There's 118 on the table altogether. How many do you think are classed as metallic? Yeah. 23. It's a lot more than 23, I'm afraid. There it is. It is 95. 95 out of the 118 elements on the periodic table are classed as metallic. We're going to think about 3 of them in particular right now. And for this bit, I am going to need 3 volunteers. People who don't mind making a fool of themselves, so adults in the room. Yeah. You can leave your earphones on your seat. And come on down, whichever stairs is closest. Come on down the middle.
Back, yeah. Just finding easy ones to get down to as well, one.
Alright, fantastic. Come on down. Okay, so what I would like the 3 of you to do is to head over to the middle here and grab one of the 3 jackets. Pop it on the front of this. Okay, put your jacket on and then grab the item that's underneath the jacket as well that corresponds with it, because you're going to be representing some of our metals. Yeah, it does leave it. That's it, grab your items off. And come stand on this side for the festival. Okay.
All these are sex.
Aye.
Things like this are real hard. Okay, you'll go first. You'd like to go to the middle for me? Okay.
Right.
Lucy, you're representing aluminium. Can you tell us anything about aluminium? What do you know about it? You can turn it into a can, absolutely. What else do you know about it? Is it heavy or light? Light, yeah. Aluminium is quite light. Is it fairly strong? You think? No? No, it's fairly soft, it's fairly easily shapeable, bendable, isn't it? What about what colour is it? Silver, yeah, absolutely. You are representing aluminium. So I'd like to give you a bit of strut, dance to the music, show everybody how you can. Go on, come on, get right to the middle, show them all. Yeah, hold it up so they can all see it. This is aluminium, it is soft, it is easily malleable, bend into different shapes, you can use it for lots of different things. Things like tinfoil, things like making cans, and even making
It is now
aeroplanes.
can music.
Fantastic work, thank you very much. Come on to this side, okay, next up. Throw it away.
The can was very naughty. It made music.
You're representing iron. What can you tell us about iron?
It's usually quite dark and quite heavy.
Yeah, quite dark in colour, quite heavy. What else? Is it strong or is it easy then?
Quite strong.
Yeah, it's quite strong, quite solid stuff. You can use it for lots of things. Excellent. If you'd like to step to the middle, straight yourself, show off the iron. We've got iron. Yeah, iron is very strong. It can be used for lots of things. It's also good at conducting electricity. It's good at conducting heat. It can be used in buildings. It can be used in railways. It can be used in cookware, like the iron pan that we've got here. Fantastic work. All right. Thank you very much. Come on to this side. What's your name? Oakley, fantastic. All right, stand right in the middle, Oakley. Oakley, you're representing gold. What can you tell us about gold?
It's very heavy.
It's very heavy.
Worth a lot of money.
Yeah?
It comes from mines.
Okay, fantastic. Well, here we have gold. Quite rare, but it's one of the rarest metals on our planet. Used for lots of decoration. Easily shapeable as well, quite soft gold. And as we said, very expensive, which is why that gold bar definitely is not real. Okay, thank you very much for taking like
Oh, done bad. Done bad. You would put it in his pocket.
I know.
Imagine they just lying there, it's real. No, I'm going to say it's not real, so they can't take it.
Okay, heading back to our periodic table then. That was a few of the metals, just a few of them. Metals have lots of... But what we're going to think about now is our non-metals. If we look to the top right-hand side of our periodic table, this is where our non-metals are.
Never mind, I'm not.
And many of these you might be quite familiar with. They are some of the most abundant elements in our universe. We're going to think in particular, first of all, about carbon. That's C at the top. And carbon is very, very interesting. I'm going to need another volunteer now, someone who is really good at solving problems, working things out. Who do we think? Alright.
Oh, Ethan.
No, it's not. Okay, come stand beside me again for me. Okay. What we're going to do is I'm going to bring over this table here, and underneath this table I've got a box with some items in. What I'm going to need you to do is to sort through these items and to work out which of them
You can
contain
eat them
carbon.
with, you know.
Okay? So, we're going to pop the box onto the table just a
It's a
second.
bit
Have a look
sauce.
through. Anything that contains carbon, put it onto the table. You've got 30 seconds. Go. Okay. You can help him out if you think he's getting it right or getting it wrong. What do you think? No?
It's the one behind you.
Yeah? Think so? Okay. What's this? That's coal. Coal contains carbon.
I must bet it's going to be all of us.
Don't know what
It's going to be all of us.
What if you've got the other side?
It's all of us.
Alright, let's have a little look at what we've got. So, these are the ones you think do contain carbon. What is this first of all? Fire extinguisher. Does it contain carbon? Yeah. In fact, some fire extinguishers contain carbon dioxide. This one does. So there's definitely carbon in this. What about this then? Petrol. Does that contain carbon? Certain? Yeah, okay, alright. Petrol is confident about that one. Then we've got coals. What do you think? Coal contain carbon? Yeah. So you put it in the right place. That's good. Alright, let's see what you didn't pick up then. What about diamonds?
If it was,
Yes.
real, it would.
If it was real, it would. Okay. Does plastic contain carbon? Well, if this is plastic, if it's real, either way, both do contain carbon. This should go on the table too. And what about
Diamond if it was real.
everything else? Does metal contain carbon? Yeah, it does as well. I'm afraid it was a bit of a trick. All of these items contain carbon. Everything in the box here. Even, yeah,
Should have just put the box on there.
But thank you very much for your help. Big round of applause. All about atoms down here. Carbon is a really versatile material. We're going to have a look at why, and this is why. How many electrons does carbon have in its outer shell then? Outside. 4. 4. Yeah, absolutely 4. Which means that it's half full. Which means that it can bond with up to 4 other elements to create various different things. It can make really small molecules, like the molecules we have in carbon dioxide, or the molecules we have in octane in petrol, which is carbon with hydrogen. It can form long crystalline chains of just carbon molecules. A diamond is completely made out of carbon, but it is structured in such a way that it forms molecules like that. Graphite in pencils, also completely made out of carbon. Carbon that's structured in a different way, lots of thin layers stacked on top of each other. But carbon can also form much bigger molecules. It can, in fact, forms the whole basis for life. Your DNA is made of long strings of carbon molecules with a few other elements that are billions of atoms long. So, carbon is a really important element. And as I said, very versatile, used in lots of things. We're going to have a look at carbon in one more form in just a second, and that is this form just here. This is carbon in the form of carbohydrates. This is sugar, basically. Can anyone tell me what are the 2 other elements in a carbohydrate? Any ideas?
Oxygen.
Carbon is one of them. Carbon is in it, definitely. There are 2 other elements as well. What else is in carbohydrates? Hydrogen is one of them, and
Oxygen.
oxygen, yeah. We can work that out from the name carbohydrate, carbon means carbon, and hydrate. When we talk about hydrating, we talk about water, H2O, hydrogen and oxygen. What we're going to do now, though, is we're going to add some acid, some sulfuric acid, to our sugar. And we are going to, yeah, it is a strong acid, and we are going to dehydrate the sugar. We're going to remove the water, and what we should end up with is just the carbon. Element of carbon. So we need these on. Here we go.
I'm very shaky.
Give it just a second.
It looks like milk. It's like poo-poo. Whoa.
And there we have elemental carbon.
That must be very hot.
What's happened here is that the acid has caused the sugar to dehydrate. It has removed the water, and because this reaction is exothermic, it produces heat. That water has then boiled away in the steam which is rose up, and what we're left with is elemental carbon. Alright. Okay, let's see. Next up, we're going to have to think about this is group 18. It's right at the far right-hand side of the periodic table. And these gases are known as the noble gases. When the periodic table was first written back in the 1800s, Dmitry Mendeleev created the periodic table and it didn't have any of these gases on it. Can anybody take a guess at why? Because they weren't found.
Oh, that smells funny.
Yeah, they hadn't been discovered at that time. Why hadn't they been discovered, I think? Yeah. True, there are lots and lots of different atoms, but when you talk about all the others, why didn't we know about these ones?
Yes,
Possibly, although they had scientists who could put all the other elements into the periodic table. So, what do you notice about the outer shell of each of these atoms? Everybody see it? Yeah. Probably is it?
Oh, it's the can now.
The
Gas can. That we said was going to explode and kill us.
Yeah. Okay. So helium, slightly. Helium's got 2 because helium's only got 1 shell, like hydrogen. 2 is the full shell if it's the first shell.
Oh,
But you actually write all the others. Excuse me. All of the others have 8 electrons in their outer shell. If they've got 8 electrons in their shell, that means that shell is full, which means that they are stable atoms. They don't react with anything. So, the reason that they weren't included in the periodic table is because they hadn't been found, because they didn't do anything. Just because they weren't reactive, though, doesn't mean that they're not useful. This is helium. Can everybody tell me what to use helium for? Yeah?
Making your voice squeak.
Making your voice squeak.
Blow up balloons.
You can use it for making your voice squeak. It's not advisable though. It's not very good for you. You shouldn't really do it. Blowing up balloons. Yeah, absolutely. We can use helium for blowing up balloons. Now, we can also use helium for keeping things cool. It's really useful in things like MRI scanners and superconductors as a cooling system. And it has one very interesting property. What's going to happen to this bubble?
It blow up. It's gonna go. Woo. You know what? Because it's helium,
Yeah.
the bubble's gonna pop off and it's gonna go up.
Yes, because it's helium, the bubble is going to come off the end and it's going to rise up. If I can get it to do it without popping.
Please don't pop.
That's going to float up into the air. Because helium is much lighter than air. In fact, if we're being precise about it, it's much less dense. Right, one more time.
How big can you make it?
How big can I make it? I don't know. We'll find out.
Well, let's find out.
About that big. Yeah, helium is much less dense than air, which means that just like a beach ball in a pool, it will always rise to the top. Okay.
Clever disco.
Alright, finally then, we're going to think about just one or two more of our elements. We're going to move on to think about this one up here, nitrogen. Nitrogen is really important. There's a lot of it on our planet. In fact, about 80% of our atmosphere is nitrogen. What do we think will happen then if I tell you that nitrogen has 5 electrons in its outer shell? What do you think about how it's going to react? What if we add fire to nitrogen? What would happen? Bit of a flame, do we think?
Blue flame.
Blue flame? Do we think we're going to get an explosion?
No.
No? Should we find out?
I think it's flammable.
Now,
I think
nitrogen, usually, as we said, it's in our atmosphere, is usually a gas. At the moment, though, what I've done is I've cooled our nitrogen down. Cooled it down to about minus 196 degrees Celsius.
Is it that
Which
freezing
means
stuff? Oh, that ice.
Dry ice.
Really
Dry
cold.
ice. Dry ice.
Oh
this
yeah.
nitrogen
Oh yeah.
in its liquid form.
It's gonna bubble.
So, let's see what happens if we add a bit of fire to our nitrogen. There we go.
It's just gonna smoke.
Yeah.
Smoke, you think?
Yeah, it's
gonna
just
smoke.
gonna reflect off. The smoke's just gonna
It's gonna really big smoke.
You sure you want to do this? Yes. Yeah, alright, here we go.
Can be
Ready,
continued.
and nothing. Nothing at all.
Oh,
Nothing at all. But why? We said it's got 5 electrons in its outer shell. But if you have a look at the structure of nitrogen,
You froze up. You froze them up.
what can you see about these 2 nitrogen
They meet.
atoms? How many electrons are they sharing? Yeah.
2, 4.
It is 6. They are sharing 6 electrons. So nitrogen doesn't exist as a single atom. It exists, like similar to hydrogen and oxygen, as a dinitrogen molecule. 2 nitrogen atoms bonded together. And they are bonded together with 6 electrons, which means they've got a triple bond. Which means that, like our noble gases, they are fairly stable. Now, we said nitrogen makes up about 80% of our atmosphere. Can anyone tell me what gas makes up the other 20% roughly?
Oxygen.
Oxygen, yeah, absolutely. Oxygen fires. It can cause death and destruction. And what we're going to do now is we're going to use our nitrogen, which we said is about minus 196 degrees Celsius, to cool down our oxygen.
You freeze the Cheetos and they're like, it'd be like dragon's breath.
Baking soda and vinegar is another explosion.
Okay.
What is he doing? He's gonna
So,
kill us all.
what we've got over here is we've got our liquid nitrogen at minus 196 degrees Celsius. We have connected it up to this copper tube with oxygen gas. And what we're going to do is we're going to pump some oxygen gas through our liquid nitrogen, which is going to come out this end. Now, oxygen condenses into a liquid at about minus 184 degrees Celsius. So what we should end up with is liquid oxygen at the end. What do we think liquid oxygen is going to be like?
See-through.
Let's find out. This does take a minute or two
Gonna
to
look
get
like
going,
water.
so I'm going to put on some very distracting music for you.
Hey, fuck off.
Bear with me as I get this going.
Dun, dun, dun. Dun, dun. Can you see that?
No.
Right down. All I can see is a perfect angle of what he's doing. Oh, there's smoke coming out from the bottom.
So, you may have been able to hear a bit of bubbling. Our nitrogen is actually boiling away at the moment because the oxygen is causing the nitrogen to warm up and it is evaporating back into the gas you can see all coming on. But it is also cooling down the oxygen gas, which is now condensing into a liquid, and we are getting some liquid nitrogen, liquid oxygen, sorry, in our beaker that's down here. We need just a little bit more, so we're waiting just a little bit longer until we get enough liquid oxygen. Almost there.
It's very blurry for some reason. It's very cool.
Okay. Alright, in our beaker we now have some liquid oxygen. What you may be able to notice is it looks like it's a pale blue colour. And as we said, it's currently at about minus 184 degrees Celsius. So, to make sure. That's okay, that's just a bit of gas escaping in here, don't worry. Alright, we'll make sure that's all safe first of all, and then what we're going to do is we're going to pour our liquid oxygen onto our crisps just here, and then we're going to ignite them and see what happens. So as we said, oxygen can be quite dangerous. What I will give you a warning is this is going to be quite bright, so if you are sensitive to bright lights, just be prepared.
I'm
Here
strong.
we go.
Oh, whoa.
Abbott's not bright, this bit's about to be bright.
Why can't we eat the cheese first? Or cheese first?
You're not going to want to eat them right now, they're very close. Here we go, ready?
Whoa! That's bright. I can feel it. I felt that. Again. That's bright.
Energy is in your body.
That I was trying to be that bright.
Our liquid oxygen and igniting our energy that was inside our crisps just then was released very, very quickly. Lots of very, very fresh flames. Alright, that does bring us to the end of our show for today. I do hope you've enjoyed yourselves, hope you maybe learned something, and I hope you enjoyed the rest of your day.